Welcome back to Differential Equations. In this lecture, we're going to learn how to solve non-exact differential equations. Before going through this lecture, make sure you feel comfortable solving exact equations. We'll be building off of that and referring to that. All right, at the end of our last lecture on exact equations, we were presented with this example. And we went through a procedure to solve exact equations. And when we came across this one, what we noticed is it is not exact. So we're left with this question, which we will answer. How do we solve non-exact equations? They are solvable, but they require something else. The something else, you can see in the title, is going to be what we call an integrating factor. And we'll go into detail about what that is. So this question is going to have two answers. The first answer, which I'll call the simple answer, is we're going to take a non-exact equation and do something to make it exact. The more complete answer of what we'll be doing is we're going to multiply the differential equation in differential form, m dx plus n dy equals 0. We're going to multiply that by a function, mu, so that's the Greek letter mu there. And our hopes is once we multiply our original differential equation by mu, we would want this new equation, mu m dx plus mu n dy equals 0, that would now be exact. Our goal is to figure out what this function mu is, called the integrating factor. And mu in general, like m and n, can be a function of both x and y. All right, before we proceed, this is a good spot for us to introduce alternate notation for partial derivatives. Think back to your Calc 1 course when you were given the first expression for a derivative, probably dy over dx, differential notation. You found it was probably more convenient in class and in solving problems to write that derivative as y prime. In a similar fashion, we're going to express, instead of using partial differential notation, we're going to express the differentiation variable not as a prime, since we have two variables to differentiate with respect to. We're going to denote the differentiation variable as a subscript. So f sub x, that denotes a partial derivative of f with respect to x, and f sub y denotes a partial derivative of f with respect to y. All right, we'll also translate our criteria for exactness from the previous partial differential notation on the right to this slightly more convenient shorthand notation for partial derivatives. All right, when you're ready, let's proceed. We're going to figure out and derive basically a formula for mu. All right. So what we're going to do is start from the beginning and assume our ODE, m dx plus n dy equals 0, is non-exact. We know how to solve this if it is exact. We're going to assume from here on out that those partial derivatives for m and n with respect to y then x, respectively, are not equal. All right, our goal right now is to derive a formula for mu. Now, you can skip ahead, but I know many of you are interested in kind of understanding at a deeper level where these things come from, so we'll go through kind of an informal mathematical proof on where the formula for mu comes from. All right. First, we're going to take our original differential equation. We're going to multiply it by a function of x and y, perhaps, mu. So we get this new differential equation, mu m dx plus mu n dy equals 0. All right. Our goal is to figure out the correct formula for mu so that this new equation is exact. Now, what would it mean for this new equation to be exact? Well, multiplying by mu, we now get new functions, which we'll call m sub 2. So m sub 2, the new n, is mu times the previous m. And likewise for this new function n, what we'll call n sub 2, which is mu n. Very easy to get confused with new, like N-E-W, and mu, M-U. I'm trying to carefully pronunciate everything. All right, so our criteria for this new equation to be exact is written down there. It's exact if the criteria for your new m and n, m2 and n2, is satisfied. What we're going to do is find a formula from mu such that this occurs. We're going to kind of work backwards from here. All right. So let's basically go ahead and say that, all right, we want this criteria for exactness to be true. So we would want these appropriate partial derivatives with your new m and n to be equal. Keep in mind right now, we're going to pretend and imagine that we know what m and n are, but right now we don't yet know what mu is. All right, so we get to here. This is our criteria for exactness being satisfied for our new functions m and n, m2 and n2. All right, well, to calculate these partial derivatives, mu times m and mu times n, mu, m, and n are all functions of x and y. How do you differentiate a product? You use the product rule. So we're going to kind of calculate the left and right-hand sides of this criteria for exactness using the product rule. Some of you are probably comfortable implementing that. Maybe pause and give yourself 10 seconds to work out the right and left sides of this criteria for exactness. All right, so if we proceed, we're going to implement the product rule. In terms of notation, I'm going to express the partial derivatives with our new subscript notation. So if you apply the product rule to the left side for mu m and its partial derivative, and apply the product rule to the right side for the partial derivative of mu n, we should get to here. And this is actually what we call a partial differential equation for mu. We are learning for our course how to solve ordinary differential equations. What we have just done is, instead of simplifying the original equation, we have complified this equation. I think I just made that up, but we've turned our original equation into something more complicated, now a partial differential equation. Take my word for it, these are extremely hard to solve within physics and engineering, and they are extremely hard to solve in mathematics, where there's very little results for partial differential equations compared to ordinary differential equations. Now, how do we recover? We're going to introduce what's called a simplifying assumption. We're not going to try to prove where this comes from, other than a physics point of view of, for mathematics, we do something because it works. And this simplifying assumption, well, it works. All right, the simplifying assumption we're going to make is, instead of supposing mu depends on both x and y, we're going to suppose mu only depends on x. Now, what effect does that have? If mu only depends on x, the partial derivative of mu with respect to y, remember, a partial derivative with respect to y, x is a constant. That partial derivative of mu with respect to y would be 0. The partial derivative of mu with respect to x would then just be mu prime, or d mu over dx. All right, now let's go ahead and use that simplifying assumption above there. The partial derivative of mu with respect to y, that's what we have expressed there as mu sub y. That's then going to become 0 because of our simplifying assumption that mu only depends on x. We're going to replace mu sub x with regular differential notation, d mu over dx. All right, let's go ahead and implement that, plug that in. And what we now have is what we are learning about. We now have, instead of a partial differential equation, that simplifying assumption has converted this back to an ordinary differential equation, which we can solve. Now, what I'd like some of you to do, and I'm sure some of you are up for the challenge, this differential equation for mu can actually be solved by separating. So see if you can continue from here to solve for mu. Keep in mind, you're going to suppose you know what m and n are, which then means you know what m sub y and n sub x are. See if you can pause and finish the proof here for the formula for mu. We'll pick up in a few seconds. All right, welcome back. Hopefully you made an attempt. If not, that's okay. This is not an exam question. I won't ask you to prove and derive where the formula for mu comes from. We're just going to continue working through that so you can see all the mathematics behind the scenes, where these formulas might come from. All right, first, I'm going to try to get all the mu terms together. I'll subtract mu times n sub x to the left side. I can factor mu out from the left side. And from here, should be very easy to separate. Multiply dx to the left side, divide by n, and then divide by mu. All right, at this point, we should be able to get rid of the differentials. This is now separated. And we should be able to integrate both sides. I want to point out here, in order for this simplifying assumption to work properly and for it to separate correctly, everything on that left side must only contain x's, and everything on the right side should only contain mu's. So we'll see that come back, that the left side there can only depend on x due to our simplifying assumption. All right, if we continue, we're going to integrate. Since we don't know explicit formulas for for m sub y and n sub x, we can't really evaluate that integral on the left side anymore. But what we can do is evaluate the integral on the right side. That should turn to natural log of mu. And to get an actual formula in terms of mu, we can exponentiate. So we get this nice formula for mu in terms of the partial derivatives of m and n, and an integral up in the exponential. All right, now everything prior so far has been leading up to where this formula comes from. So here's the proof. We just worked through it. Let's go ahead and summarize, since there are probably some of you that really don't care where these formulas come from. Professor, just give me the formulas that give me the solutions for the exam questions, right? Okay. So let's go ahead and summarize what we just went through. We're going to address here an integrating factor, mu, for non-exact ODEs. All right, and it's a pretty simple formula. We just have to calculate it correctly. You need to properly identify m and n and calculate your partial derivative of m with respect to y the partial derivative of n with respect to x. You would probably be doing that anyway to verify if it is exact to begin with. If it's not exact, you already have all the work here to calculate this formula for the integrating factor. All right, now let's point out what I talked about in the lecture, but we'll make it more precise. In order for this formula to work, our simplifying assumption was that mu only depends on x. That means now that this fraction in the integral, that also must only depend on x. Now, there is an alternate version if our assumption that it only depends on x was wrong. We could alternately suppose maybe it depends only on y. I'll leave the proof and the work maybe for you to implement, very similar to the work that we just went through. But now this expression, n sub x minus m sub y divided by m, that must only depend on y. Now between these two versions, the first one, due to the assumption that mu only depends on x, that's going to be a little more useful and frequently used, but it's good to be familiar and comfortable with both. All right, so how do we actually then use our integrating factor mu to solve this ODE? We're going to give an overview, what to do if it is exact, and then what to do now if it's not exact. So our goal right now is to solve an ODE in differential form. All right, ideally, this is exact. If this differential equation is exact, we solve these two equations to figure out the function little f that we've been using notation-wise in the previous lecture. All right, and that we summarize as we're going to integrate one equation, compare with the other, and it falls into place. All right, now what do we do if it's not exact? First step, remember we're going to make a non-exact equation exact, and we do that by finding an appropriate integrating factor. So step one, we're going to find an integrating factor mu. We have two versions above. The one in the box, the function only of x version, that'll be a little more useful. All right, the second step is once we have mu, we then multiply our original ODE by mu, and we can solve these two equations for the new m and n. And recall that your new m and n are now mu m and mu n, referring to the original m and n from the original ODE. All right, now the only thing new here is getting the integrating factor, and it presents a little bit more work. But once you get down to step 3 there, it's the same steps and procedures and ideas that we used in the previous lecture for solving exact equations, just with the extra step of putting in an integrating factor. All right, when you're ready, let's get to some actual examples. Okay, I'm sure some of you feel confident with the course material so far. So if you'd like to pause to make an attempt at this, give it a try, and I would say maybe give yourself 5-8 minutes or so. If you don't feel comfortable, just continue with me right after this. I'll pause in case you want to pause to work on this. All right, either you made an attempt or you're just waiting for me to go through it. Let's go through it. So first we would identify m and n. Okay, and we would want to check if it is exact, but from our intro, we already know this is not exact. Those partial derivatives are not equal. All right, so what we can do is use maybe our first formula for the integrating factor, the function only of x part, m sub y minus n sub x divided by n. And we are careful with our signs, using parentheses from the subtraction sign. And then we notice the end result, x plus y divided by x squared plus xy, that's not just a function of x. There's y's in there as well. Now be careful, this is going to happen a lot where you have something that looks complicated. Simplify it. Give you a few seconds if you want to pause to simplify that expression. All right, what can you do to that? Well, notice in your denominator, you can factor out x. Then the factor of x plus y cancels out, and we get what we want. This expression does only depend on x. All right, now this by itself is not mu. We have to take this expression, integrate it, and then put that in the exponent of the exponential function. All right, so we get here inside the exponential function, the integral of 1 over x, which we know integrates to natural log of x. E raised to the natural log of x cancels to x, since the exponential function and the natural log functions are inverses, they cancel. Okay, so far we have our integrating factor, mu, which is just x. So we take our integrating factor, mu equals x. We go back to our original differential equation at the top there. We're going to multiply the whole thing by x. Now there's some work here in red. You might be questioning, shouldn't we be including an integration constant, a plus c? Well, it makes no difference. If we did include the plus c there, notice it just simplifies to give you your kind of slightly different integrating factor, a constant times x. We're only interested in the function part, x, not that constant multiple. We can just divide by that constant multiple to get rid of it, but x is needed to make it a correct integrating factor. All right, so let's multiply our original differential equation by x, and we get our new ODE. All the terms in there have been multiplied by x, our integrating factor. All right, what I'd like you to do is verify that this is now exact. I'll save that work for you to work out, but it is exact, which means we can jump to our two equations here to solve for little f, the potential function. All right, this is actually straightforward compared to some of the examples from the previous lecture. So I'll leave it to you to go through and solve that. What you should get at the end is your f of x and y. You should get it as x cubed y plus 1/2 x squared y squared. All right, and that's how we relate our previous lecture topics. Solving exact equation, that comes back right here. So likely if you're encountering any difficulties from here, I would say go back to address how to solve exact equations. The only new part here is the integrating factor. All right, if you're ready, let's take a look at a different example on how we use an integrating factor. Let's take a look at example 2. All right, ideally, I'd like you to make an attempt at this. Pause, give yourself a little more time. I don't know, maybe 10 minutes, maybe more. This one has some more tedious calculations involved. So pause, give yourself at least 10 minutes, and check in after that. It's only more difficult due to the integrations and calculation of certain partial derivatives. We'll check in about 10 minutes. All right, welcome back. If needed, make sure you go back and review and have in your notes the formulas for the integrating factor. That's going to be your starting place for these if they're non-exact. All right, so what you should find here is you get as your integrating factor, mu, should come out to be e to the x. All right, you end up integrating 1. The antiderivative of 1 is just x. So we get as our integrating factor e to the x. Okay, we're going to use that integrating factor, multiply your original ODE there in the statement of example 2 by e to the x. All right, and we now have our new m and n, which have been multiplied by e to the x, and we need to solve these two equations. Now, this is where most of the time is going to be spent. I would advocate to integrate equation 2 here with respect to y. And the reason for that, notice equation 2, that right-hand side, it only depends on x. There's no y's. That means that whole right-hand side is a constant with respect to y. So the antiderivative would just be that constant times y. All right, this is also complicated to solve these two equations because you would compare with the first equation, you'd have to use the product rule. Since you'd be differentiating with respect to x, and x plus 1 times e to the x, you'd have to differentiate that using the product rule. Now, if you go through and solve these two equations correctly, there's a good amount of work, but it's just more or less being careful implementing the product rule correctly. You should get your function of x and y as this. And that is our solution for example number 2. This is a great one to follow up with me on during virtual office hours if you were getting stuck and couldn't get some of the steps to work out correctly. All right, that concludes everything I wanted to go through for using integrating factors for non-exact differential equations. Make sure you're comfortable with both versions for the integrating factor mu, slight preference given for the version assuming mu is only a function of x.